Hello, thank you for joining my talk. Today I want to discuss a problem related to oriented percolation, specifically to the number of open paths. This is a joint work with Ryoki Fukushima. Now first about the setup, and here I first want to clarify that whenever I say path, what I mean is a nearest neighbor directed path on the integer lattice in arbitrary dimension. So here there is an example in dimension 1, starting from the origin with time drawn downwards. The setup is directed or oriented in the sense that the path cannot go backwards in time, which is what would be allowed in normal non-oriented percolation. In addition, we have a random environment whereby each space-time site is either open or closed, independently with probability p. On the left, this is indicated by black and white dots, the white ones being open. And as usual in percolation, we define a path to be open if along the whole trajectory there are no closed sites. This is one example here. One way to think about the model is that the closed sites are obstacles that prohibit the path from going into certain areas. For example, this area here is unreachable because the path has nearest neighbor steps and therefore cannot cross this wall of closed sites. Now this is a very well studied model, and the classical result here is about the existence of a phase transition for the event of percolation. That is, for the event that there exists an infinitely long open path. Namely, this probability is strictly positive if and only if p is above a critical value. In the following, I will always assume that this is the case, so I only discuss supercritical oriented percolation. There are many similar results in the literature which concern the existence of long open paths satisfying certain properties. One example is a shape theorem, which guarantees the existence of open paths with positive speed. Namely, on the event of percolation, with very high probability, you can find an open path pi whose position at time n moves away from the origin at positive speed. The question that I'm interested in today is a slightly different flavor, namely, I'm interested in the behavior of typical paths. What do I mean by typical? I mean a path chosen uniformly at random among the set of all open paths of a certain length. It turns out that such paths have a quite different behavior than the kind of paths that appear in existence results. Just to give one example, there is a conjecture that the position of such a uniformly chosen path at time n, this position moves away from the origin sublinear. So very different from the positive speed behavior that we have before. Now let me tell you about our results. They are about this quantity, the number of open paths of length n. And the motivation for studying this quantity is that if we want to understand some combinatorial object, say this set number of open paths of a given length, then usually what you first do is try to count how many elements it contains. In this case, there is some previous result which tells us that the number of elements grows exponential with a deterministic rate. More precisely, there exists a constant alpha, strictly positive and depending on the parameter, of course, such that the number of open paths grows exponential like n times alpha plus smaller order terms. And here the mode of convergence is that it's almost surely on the event of percolation. Now you need to restrict to this event because on the complement there is no infinitely long open path, so this quantity here will be 0 eventually, and therefore there cannot be exponential growth. Now one word about the proof, and here you want to consider the following approximating sequence. You take the number of open paths of length n, then take its logarithm and integrate over the environment. And this is an approximating sequence that you can then apply the super-additive lemma to. Here there is a complication in that we also need to condition on the event of percolation. If we don't do this, then this quantity here may take the value minus infinity. It turns out that conditioning on percolation is quite a bad operation because this sequence here is not strictly speaking super-additive. So in the paper they had to create a new procedure to deal with this issue and to work quite hard to get the result. Now, one drawback of relying on the super-additive lemma is that you can only conclude the existence of a limit. So you can conclude that the growth rate alpha exists, but you cannot say anything about the smaller order terms here, and you also cannot say anything about the dependence on the parameter p. And these are the 2 points we wanted to address in our paper. And before I show you the result that we managed to prove, I will discuss the following technical ingredient, which is a concentration inequality. So it tells you something about the probability that the log number of paths is far away from its expectation. Remember that this expectation here is precisely the approximating sequence that was used to define the growth rate alpha, which is the quantity that we're really interested in. Now, our result says that the probability for having a deviation of this order is bounded by a polynomial with an arbitrary large exponent. And the order of the fluctuation is n to the 1/2 plus an arbitrarily small epsilon. Note that both of these quantities here are typically of linear order, so this fluctuation here is really a small fluctuation. And as before, we again need to condition on the event of percolation, because if we don't, then you have minus infinity with a positive probability here. I don't have time to go into details of the proof, so let me just quickly mention a few of the technical obstacles. And the first one here is the model is very rigid. And what I mean by that is, well, first we have considered only nearest neighbor paths. And here I should mention that there are some previous results in the literature which are quite similar, but they are for models that are either in continuous time or in discrete time, but with arbitrary step width. And both of these changes make the model much easier to analyze. In addition, we've restricted to paths that are either open or closed. More precisely, a path is closed as soon as it contains a single closed spacetime site. And that means that if you flip a single spacetime site from open to closed, then potentially you change a large number of paths from open to closed. And this is quite difficult to deal with because it means that a single spacetime site can have a very large influence on the outcome. So that makes it very unlikely that concentration holds. Now, one way to deal with this rigidity would be to apply finer properties of the model. For example, if we had access to the law of large numbers that I mentioned on the previous slide, then we could give a fairly short proof for the concentration inequality. Similarly, if we had some information about how fast paths typically move away from the origin, then you could also give a fairly simple proof. Now finally, let me actually tell you what our concentration inequality can do. And here I want to emphasize that we have a very good control on the constant that appears on the right-hand side here. In particular, we can show that the constant is uniform in the parameter of percolation. More precisely, you can use the same constant on the right-hand side for all parameters as long as you bound it away from the critical value. One consequence of this is that the growth rate alpha depends continuously on the parameter. Now, how does that work? So you have to show that alpha of q converges to alpha of p as the parameter q converges to p. And remember that the growth rate is defined with the help of this approximating sequence that you apply the superadditive lemma to. That means you quickly end up with this double limit here. So first taking time to infinity and then changing the parameter of percolation. What our uniform concentration inequality allows us to do is interchange these two limits. And once you have justified this, you're in fact done, because as long as time is fixed, this quantity here is clearly continuous. Namely, it depends only on a finite number of random variables, so you can, for example, use dominated convergence. So the real technical step is to justify interchanging the limits. So there are some further results that we can prove using our concentration inequality, but I'm out of time. So I'm looking forward to seeing you in the Q&A session. And if you're interested, I also invite you to have a look at the archived version of our paper. Thank you.